A very good afternoon to all of you. And now I would like to continue my discussion on the philosophical foundation of quantum mechanics. And I think this was the last slide in the previous video where we were talking about the breaking down of classical mechanics. And we could see that there is a sharp transition uh, uh, when we go down to the microscopic scale, the scale of atoms, the scale of molecules, the scale of subatomic particles, uh, uh, where this classical mechanics, it breaks down, it fails to explain some of the important parameters that are linked with the dynamics of these particles. And at the same time, uh, uh, we could infer at this point of time that to take care of those things that couldn't be explained using classical physics, the quantum mechanics seems to be a gateway, even though it's not a kind of gateway that can completely take us to that complete reality that we want to understand. But certainly, the quantum mechanical principles they provide a good state of understanding these systems at the quantum level, at the microscopic level. And at the same time that we have been talking about the velocities, when the velocities of the objects uh, is comparable to the speed of light, the classical mechanics fails, the Newtonian mechanics fails, and you replace this mechanics to explain some of the important behaviors and some of the important physical quantities that are assumed to be absolute in the Newtonian domain, like mass, time, and dimensions of an object. They seem to have some relativistic relations. So to proceed from here, so the, in, the, the introspection here is that we want to extend this phase of understanding that how this classical mechanics fails in explaining some of the important phenomena of the nature. Now, if we take into account, you can see that this photograph, you can see this is the black body radiation. What's a black body? A black body is something on which you suppose you bombard some radiation on a black body, it will absorb all the radiations ideally, or I should say in reverse of this action, if we have a body that emits all the radiations, that body can also be considered as black body. And there is no ideal black body in nature. We don't have a black body that can absorb all frequencies, that can absorb all wavelengths, but we can take some of the objects as close approximation to the black body. And in this photograph, you can see that you presumably assume that some radiation passes through this hole, and there are multiple reflections that are taking place to this radiation, so that there is no place left for this radiation to come out of this ideal black body. And this can be a good example, this can be a good ideal example to understand what black body is. So the point is that if you have a body that absorbs all range of frequencies, that absorbs all range of wavelengths, we call this body as the black body. Now, what was why was it that classical mechanics failed to explain the black body radiation law? If you rightly remember, there are some basic laws in classical mechanics. I mean, what the Wien's displacement law is there. Stephen's law is there, and there's Rayleigh-Jean's law. And these laws are all the time used to explain the problem of black body radiation. Even though these models, these classical models, they explain only some portions of this black body. One, say for example, if I talk about Vane's law, it fits in some particular region, and then Stephen's law and Rayleigh-Jean's law, it fits in some other domain. And there is one fundamental problem in classical laws to explain the absorption of the radiation or the emission of a black body radiation. That is what is known as ultraviolet catastrophe. What ultraviolet catastrophe is that if you have the incident energy that's falling on this black body, as you go on increasing the frequency of the electromagnetic radiations, this curve should go to infinity. This is what is called as ultraviolet catastrophe. And the photograph that you can see here, this photograph is telling us that this is how experimentally a black body which is close to an ideal black body reveals. And we can see that there is a variation, and there is decrease in energy. So this is the experimentally observed behavior of a black body, the experimentally calculated behavior of a black body, which is an approximate black body. And to classical physics, there is no explanation. There is no explanation for why we are observing the curves like this. And you can see the curve going up, then coming down as you increase the wavelength of the incident radiations. Classical physics fails to explain this kind of behavior. It's a failure of the classical mechanics. And what Newtonian physics believes here, the basis of the Newtonian physics in this domain is that the electromagnetic radiations, they are the continuum radiations. They have a spreading nature. And all of those concepts are used to explain the behavior of a black body. But all of those classical concepts, they fail to explain this experimentally observed curvature that you can see between the energy and the wavelength. And to answer this question is resolved by Max Planck, who presumably assumes the quantum nature of light. Because in classical world, we have waves and we have particles. In classical world, the particles are a separate identity, and for particles you have all possible and plausible equations that can describe that particle. But at the same time, the waves, they are a different entity. They are not linked with the particles. They are treated in a different mathematical domain. So in classical world, you have particles, they are particles, and you have waves, they are waves. They are independently following some mathematical modes. They are independently following some mathematical models to be described, their existence, their generations, their propagations, and whatever is linked with those waves. But the point here is that in explaining the Planck's black body radiation law, the classical laws, they fail to explain this kind of behavior. And what is the basic reasons for that? The reasons for that is that the classical domains, they treat waves as a different identity. they treat that light is an electromagnetic wave. It has a nature of spreading, and using the postulates of nature of spreading of this wave, they fail to account for what's called as Planck's black body radiation law. And this problem is resolved by Max Planck, and he resolves this problem by articulating the particle nature of light. So what I said, there is the two identities like waves and particles in classical physics, they are separate identities. And a particle is always a particle here, a wave is always a wave here. And treating this problem by assuming the particle nature of light, the Max Planck was able to obtain the behavior on the basis of his postulates. And one of the important postulates of the Planck's black body radiation law is that the black body absorbs energy. It absorbs energy in the form of quantas, and each quanta has an energy E. Each quanta has an energy E equal to h nu, where h is called Planck's constant, and nu is the frequency of the photon. So Planck comes up with this argument. He uses this argument, and he exactly predicts the behavior of the black body. And if you plot down the theoretical model that's prescribed by the Max Planck, that model is very close to the experimentally observed data, which completely contradicts the classical laws like Rayleigh-Jean's law and Wien's law. It completely goes against those established laws in classical physics. So here you can say that this is the failure of the classical mechanics to account for the observed spectrum of the black body radiation. The next important effect and what light is treated, I mean, when we do the classical experiments based on light in our laboratories, we perform the experiments of double slit experiment, we perform diffraction experiments, we perform polarization experiments, and all of these experiments, they reveal that the light that's coming from the sun, the light is an electromagnetic wave. The light is a wave, and it has a nature of spreading. And in the classical domain, when you talk about the wave nature of light, it's a complete description of the classical physics. Classical physics is completely able to describe the wave nature of the light. So there is no articulation in front of the classical physics to account for some other nature of this light. Because as I said previously, that there are two different frameworks that are working in classical physics. One framework is for the particle nature of the particles, and the other framework falls in the wave nature, something that's waves, the wave that we produce in water, what we call as water waves, the sound waves that we produce by when we have a guitar in our hands and we go on banging that guitar. So these are so classical physics has a complete independent description for these kind of things. But here at the same time, so classically you are describing the wave nature. Light is an electromagnetic wave. It's a wave, and it's confirmed by the interference experiments where we obtain those fringes, dark and bright fringes, confirming the wave nature of light. Then taking into account the diffraction experiment that we perform, that again confirming the wave nature of light, and polarization experiments where we bombard the light and then we change the domain, we change the orientation of some crystal, and that again can be accounted for the wave nature of light. And the same argument is tried to explain a phenomenon what's called as photoelectric effect. So classically, if classical mechanics is applied, if Newtonian physics is applied to a phenomenon like this, what's called as photoelectric effect, if you have some kind of photosensitive metal and you bombard this metal with some specific type of radiation, say ultraviolet rays, when ultraviolet rays fall on this metal, you have emission of electrons. And this emission of electrons, due to the bombardment of light on this material, this is what is called as photoelectric effect. This is the electrons that are emitted from this metal have they come out of this metal because of the radiation that falls on this photosensitive metal. And if we have to explain this kind of behavior, because here we have an important argument in classical physics. The argument is that that if you increase the intensity of the radiation that's falling on this material, then on increasing the intensity of the radiation, at any point you can obviously emit the electrons from this photosensitive metal. And keeping in view at the same time, as I said before, that light in classical domain is a wave. So if light is a wave, it has a spreading nature. And if it has a spreading nature, then the light that falls on this metal, it is going to spread on this photosensitive metal. If it spreads on the photosensitive metal, and if we make some minor calculations, these calculations reveal us that the amount of energy that one electron, which is a free electron in this photosensitive metal, the energy that can be distributed to that one electron in this material is extremely low. It's impossible for that energy to get this electron out of this photosensitive metal. So treating this kind of effect, treating this kind of phenomenon, classically, it is impossible to explain photoelectric emission. As I said you that if you treat it a wave, even if the intensity of this wave is high, even if the frequency of this wave is high, the energy that's absorbed by one electron, which is free in this kind of metal, it will be extremely low. It will not be enough energy that it can have so that it can leave the potential barrier of this metal, and then it will have some kind of kinetic energy. So this is one argument, what completely fails to explain why there is at all why there is at all an electron emission from this metal. And there is another important argument. That argument is that when you perform this experiment, the electron will come out only after the incident electromagnetic radiation has frequency greater than that of some minimum frequency, and that minimum frequency is called as threshold frequency. So you will not have any photoelectric current even if the intensity of the light that's falling on this metal is doubled, tripled, quadrupled. The electron is not going to come out, but once you make use of the radiation whose frequency is greater than that of this threshold frequency, the photoelectric emission takes place. So, as I said, the classical argument fails to explain the photoelectric effect. And fundamentally, in classical world, light being an electromagnetic wave, the theory of waves will extremely fail to explain this kind of phenomenon that we observe in our laboratories. And to answer this question was answered by Albert Einstein, and probably this was the answer to this problem led Albert Einstein to have a Nobel Prize in Physics, which is purely quantum mechanical in nature, even though we'll see that Albert Einstein was not completely comfortable with arguments of quantum mechanics, the arguments of entanglement, but this great personality received Nobel Prize for resolving the problem of photoelectric effect. And what was the argument of the photoelectric effect? The argument was that the light that's falling on this photosensitive metal, it does not behave like a wave, the way we presume light to be a wave in classical world. But what it does basically is it behaves like a particle. It's like the particles are interacting with the metal surface, and the particles are interacting with the free electrons inside these metals. And when the particles come, they must have some energy. That energy must be greater than that of some minimum energy. And what that energy must be, h nu, and this nu must be greater than the threshold frequency, some minimum frequency that's required for this kind of observation. And assuming the Planck, so as we have already talked about, the black body radiation law, which was successfully explained by Max Planck, Albert Einstein used the idea of Planck. He used the quantum nature of light and explained the photoelectric effect quite effectively. And what we obtain here, we have an equation like the photon that's falling, assuming that a photon is falling on this metal, and this photon has the energy, say it has the energy equal to h nu, and this energy breaks into two parts. A part of this energy is used to eject an electron from the photosensitive metal, and that's what is called as work function, and that we represent as phi naught. And the rest of the energy that this photon has, which is interacting with this electron, is given to the electron in the form of kinetic energy. And the kinetic energy of the electron can be written as h nu minus phi naught. So if we write down this kinetic energy as h nu minus h nu naught, right, this nu naught is the threshold frequency, this equation explains us everything about the photoelectric emission. And we can easily see that if your photon that's falling on this material, if it has energy less, if nu is less than nu naught, then you will have kinetic energy as negative. But kinetic energy cannot be negative, therefore it is not possible for the electron to leave the photosensitive metal. But if you want photoelectric effect to happen, then the frequency of the incident photon should be greater than that of the threshold frequency, and that can be revealed from this equation. So if nu is greater than nu naught, only then you will have an electron which has kinetic energy. So the argument here is against the classical physics, where you are coming up with a new idea that's purely contradicting classical physics, that's giving you a kind of action that light can do other than that of being a wave. But in classical domain, a wave is a wave, a particle is a particle. So here you are coming up with an explanation to something that cannot be explained by the wave by the wave theory, and you are explaining this by assuming the particle nature of light, and assuming the particle nature of light leads to the explanation of one of the brilliant experiments in the history of times, what is called as photoelectric effect. And this photoelectric effect is the basis of the most of the semiconducting technology that we have been using in modern times. It is the photoelectric effect that is the part of all of these semiconductors that are working in the form of light emitting diodes, in the form of transistors, and it has certainly formulated, it has framed over time in terms of technology. So certainly photoelectric effect should take a good account of credibility. It should take a good account of it should take a good account of acceptability by the globe, because explaining this kind of argument has led to the development of science in most of the domains. So here we have another failure of classical physics in the form of the experimentally observed phenomenon known as photoelectric effect. Now, look at this. The Newtonian physics is purely, it can explain to a very good degree, it can explain the motion of the planets. And it has a tendency to explain the tilt of the planets with respect to the gravity of the sun, taking into account the universal law of gravitation, plausible to explain the motion of the planets, the motion of Earth, the motion of Mars, Venus. All of those planets can be described exclusively using Newtonian mechanics. But when it comes to Mercury, the Newtonian laws fail. They cannot explain the tilt, because the tilt in the Mercury is the largest. It has more precession. It has more precession with respect to the gravity of the sun. That precession cannot be explained using Newton's laws and using a universal law of gravitation. We fail to explain the dynamics of the Mercury, the geometrical dynamics of the Mercury around the sun. At times when you look towards the Mercury, there happens to have times when Mercury seems to be going in the backward direction, and the tilt that this Mercury has, that tilt cannot be explained using Newtonian laws. And what is more important here is Mercury has it rotates only three times on its axis, while having two complete rotations around the sun. So the dynamics of the Mercury seems to be more complicated, and it cannot be accounted by the Newton's laws. Newton's laws could not explain the motion of Mercury around the sun. And what seems to be the plausible answer to the problem of Mercury? The plausible answer to the Mercury is Einstein's general theory of relativity. And when we presume that gravity is the wrapping of space and time. So when we treat gravity as a wrap between space and time, then we are precisely able to explain the dynamics of Mercury, the motion of Mercury around sun, and at the same time using the ideas of general theory of relativity, we can account for the precession, because as I said, its precession is it's of the order of 0.2, and if we compare the 0.2 with other planets, they don't have 0.01 and something. Their precession level is very less, and that is consistent with Newtonian mechanics. Newtonian mechanics can clearly explain the amount of precession that there is for rest of the planets, but Newtonian mechanics fails to explain the large precession that Mercury has with respect to the gravity of the sun. And general theory of relativity plays a pivotal role, and it precisely explains that why there is more precession to the Mercury with respect to the gravity of the sun, by simply assuming the space-time curvature, treating gravity as space-time curvature rather than that of the force between the two bodies. So this is another argument, this is another failure of the classical physics, where Newtonian mechanics, where the classical laws fail to resolve the problem of Mercury. Now, as we have already talked about these important things, I would like to summarize the failings of the classical mechanics. And the point one, as I said, is the speed of light. What classical mechanics assumes, speeds can add up. They can add up in all states. If you have the speed equal to speed of light, then you have another speed, you are adding another speed equal to the speed of the light, then the total speed of that being must be equal to 2 times the speed of light. But relativity showed the constancy of the velocity, because the basic argument of the special theory of relativity is there is a limit. There is a limit for any material particle that is existing in this universe, and that limit is that a material particle cannot have the speed equal to that of speed of light. Maybe it can be closer to the speed of light, where you will have those relativistic effects that will be accounted for, which we'll be discussing later on. But you cannot have a material particle which can have a speed equal to that of speed of light, or speed greater than that of speed of light. And it fails in electromagnetic phenomena. Like classical mechanics don't explain the radiation that I talked about, the Planck's black body radiation, photoelectric radiation, and certainly it's leading to the quantum electrodynamics. The classical electrodynamics leads to the quantum electrodynamics, where the problems are resolved to some extent. And the double-slit experiment, when you talk about those microscopic particles that we were talking about, the patterns, the interference patterns that we can observe, which we'll be discussing in the later sessions, the double-slit experiment, where when we flourish with an argument that material particles have waves associated with them, then we encounter the double-slit experiment, and classical physics fails to explain the double-slit experiment for the microscopic particles like electrons. And classical physics has no answer for the dual nature of light. So, because as I said, the two theories, the theory of waves and then you have the theory of particles. You cannot extend the theory of particles to the theory of waves. And you cannot extend the theory of waves to theory of particles. So in the classical domain, you have these two separate identities. You are treating them independently, but now you are coming across a particle which has a dual nature. Dual means it's behaving like a wave when we perform the double slit experiment, when we perform the polarization experiment, when we perform the diffraction experiment, but at the same time, when we go with photoelectric effect, when we go with Planck's black body radiation law, when we go with Compton effect, then the same light is behaving like particles. So classical physics has no answer for the dual nature of light. So from here we will proceed in the next lecture. By now, I would like to say goodbye, goodbye, and good luck.